Next, a disk is rotating with an angular speed of omega. If a child sits on it, which of the following is conserved? So you know, disk was rotating with an angular speed of omega. Speed was constant. No force, force means torque here. No torque was acting on that. If torque was not acting on that, which thing will be conserved? Kinetic energy, potential energy, linear momentum or angular momentum? You know the law of conservation of angular momentum. If torque is absent, angular momentum should be conserved. It means we have to go with D because we have a formula. What is torque? dl by dt. If torque is 0, this leads to this result, L should be constant. If it is 0, L should be constant. Next, it is from 2003 AIPMT. A thin circular ring of mass m and radius r is rotating about its axis with a constant angular velocity omega. 4 objects each of mass m are kept gently to the opposite ends of 2 perpendicular diameters. The angular velocity of the ring will be, again same concept. Your disk was moving with constant angular velocity. Velocity is constant, you know from translatory motion. Force should be 0 and a log of force in this chapter is torque. Torque should be 0. If torque is 0, angular momentum should be conserved. What is angular momentum? I into omega. It means product of I and omega. It should be same before your event and after your event. So what was the angular momentum? It was a ring. Rotating with an angular velocity omega. If radius of ring was r, its moment of inertia was mr square. So its angular momentum was, initial angular momentum was I omega. So initial angular momentum was mr square omega. What you did now? You select 2 mutually perpendicular diameters, one and another, and you gently fix 4 masses m on the 4 corners. Distance of 4 masses from axis of rotation which was passing through center, it was r. So now the moment of inertia of system is increased because moment of inertia is not following the law of vector addition. What initial moment of inertia was there? Now moment of inertia of these 4 particles should be added in this. So new moment of inertia is now I plus 4 mr square. Mass of ring was capital M. Mass of ring was capital M. It was given. So we will denote that by capital M. And these masses are small m. These masses are small m. M. So now your new moment of inertia is equals to mr square plus 4m r square. So definitely omega will change. Let new omega is omega dash. Let new omega is omega dash. So new angular momentum means final angular momentum. It should be I omega, means I dash omega dash. What is I dash? mr square plus 4mr square. Let omega is omega dash now. But since torque was absent, Li should be equal to Lf. It means mr square omega. It should be equal to mr square plus 4mr square omega dash. Cancel r square from everywhere. Take common and cancel it. So what you are going to get? Omega dash is equals to m omega divided by m plus 4m. M omega divided by m plus 4m. So we are going with A. 33rd. A round disk of moment of inertia I2 about its axis perpendicular to its plane and passing through the center is placed over another disk of moment of inertia I1. Rotating with an angular velocity omega with the same axis, the final angular velocity of the combination of the disk is, again we got same type of problem. Initial angular velocity was omega, so initial angular momentum was I1 omega. But now you put one more disk, so now total moment of inertia is I1 plus I2. Since without applying any torque we are changing moment of inertia, omega should be changed. Let new angular velocity is omega dash. So what is the new angular momentum? Final angular momentum should be I omega dash. But since torque was not there, Li should be equal to Lf. So I1 omega, it should be equal to I1 plus I2 omega dash. So what we are getting? Omega dash is equals to I1 omega divided by I1 plus I2. So what should be the correct answer? I1 omega upon I1 plus I2. So we are going with option C. Next, a wheel having moment of inertia 2 kg meter square about its vertical axis rotates at the rate of 60 rpm about the axis. The torque which is applied to stop the wheel's rotation in 1 minute will be. First write down again problem related to equation of motion. You want to calculate torque. Torque is I alpha. I is given. Alpha is not there. So we want to calculate alpha. So which physical quantities we have to calculate alpha? Initially the wheel was rotating at 60 rpm. frequency is given, initial frequency. Frequency means number of revolutions per second, but it is per minute. So divide 60 by 60. So you will get revolutions per second. So it is 1. So what was initial angular velocity? If you have time period, 2 pi by t. If you have frequency, 2 pi f. So it was 2 pi. You want to stop this field, it means final angular velocity should be 0. In 1 minute, time is given 60 seconds. What alpha is required for this purpose? We can calculate by the equation of motion. Omega is equals to omega naught minus alpha t, because it is retardation now. Omega is 0, omega naught was 2 pi. Alpha we want to calculate, time is 60. So what we are getting? 60 alpha is equals to 2 pi. Therefore alpha is equals to pi by 30. Now easy for you to calculate torque. I alpha. I is given 2 kg meter square. Alpha you got pi by 30. So what we are getting? Pi by 15. SI unit is radian per second square. Pi by 15 radian per second square, or torque. Sorry, it is torque, not alpha. It is torque. Alpha's unit is radian per. It should be radian per second square. Alpha is torque. Torque means R cross F, Newton meter. So we got pi by 15 Newton meter. 35th. A uniform rod AB of length L and mass M is free to rotate about a point A. The rod is released from rest in the horizontal position. Given that the moment of inertia of rod about A is ml square by 3, the initial angular acceleration of the rod will be, we can calculate. We know that why rod should start rotation. Its weight is acting at its middle point. It is the force which will start rotation, and distance from axis of rotation is L by 2. So torque we can calculate. Distance between R and F, it is R, it is F, 90 degree. So torque is R cross F, means R F sin theta. R is L by 2, F is mg, sin theta is 1. So it is torque, but we have one more formula for torque, I into alpha. What is I? They gave you ml square by 3. So ml square by 3 alpha should be equal to L by 2 mg. Cancel L with L, m with m. What we are getting? Alpha should be equal to, take 3 on numerator, 3 by 2 g by L. So we are going with 3 by 2 g by L, means C option was correct. 36th. A particle of mass m moves in the xy plane with a velocity v along the straight line AB. If the angular momentum of the particle with respect to origin O is LA when it is at A and LB when it is at B, then since particle is moving in a straight line again, previously we solved this type of problem. You want to calculate angular momentum about origin. So perpendicular distance of this line from origin is always same. So angular momentum should be same, means we are going with A. LA is equals to LB. Next, a good conceptual problem. If F is the force acting on a particle having position vector r and torque with the torque of this force about the origin, then we know that what is torque? Torque is R cross F. You know the cross product properties? It means torque should be perpendicular to the plane in which R and F lies. Torque should be perpendicular to R. Torque should be perpendicular to F because it is the result of cross product. If torque is perpendicular to R, its dot product with R should be 0. Why? Theta is equals to 90 and cos 90 is 0. You know that in dot product we are using cos theta. With same concept, dot product of torque and F should be 0. So R dot T is equals to 0 and F dot torque is equals to 0. So we are going with option A. Means they want to check your knowledge of vectors plus do you know the direction of torque. Next, similar problem. A thin circular ring of mass m and radius r is rotating in a horizontal plane about an axis vertical to its plane with a constant angular velocity omega. If two objects each of mass m be attached gently to the opposite ends of a diameter, then new angular velocity should be C. Again similar type of problem. It was your ring and it was its angular velocity. So its angular momentum was initially I into omega. It was ring, so I was mr square. What you did? You put at the end of diameter two masses, one at one end, another one at this end, of mass small m. The distance from axis of rotation is r. It means you are increasing the moment of inertia. So now new moment of inertia of system should be moment of inertia of ring plus moment of inertia of these two masses. Simply we have to add the moment of inertia of all three parts of this problem, mr square plus mr square. Since moment of inertia is changed, but we want L should be constant, so omega will change in the manner to keep LF constant. Since Li is equals to LF, therefore new angular velocity is let omega dash. Therefore mr square omega should be equal to, in the absence of torque, angular momentum cannot change. So what we are getting? Omega dash is m omega divided by m plus 2m. M omega divided by m plus 2m. So we are going with C. 39th. If a sphere is rolling, the ratio of its translational kinetic energy to total kinetic energy is given by, actually it should be given, problem is little bit incomplete. Is it solid sphere or is it hollow sphere? So we will take first case, solid sphere. Translational kinetic energy is kinetic energy translational, half mv square. We are keeping it half mv square. Kinetic energy rotational, half I omega square. Since we are considering solid sphere, so it should be 2 by 5 mr square. What is omega? Omega is v by r. So we are writing v square by r square. Cancelling this with this, we are getting 1 by 5 mv square. So what we are getting? Total kinetic energy half mv square plus 1 by 5 mv square. 5 plus 2, 7 by 10 mv square. So therefore, they want to calculate the ratio of translational kinetic energy upon total kinetic energy, means half mv square divided by 7 by 10 mv square. Cancel mv square by mv square. 1 by 2 divided by 7 by 10 means 10 by 7. So we are getting 5:7. So we are going to take answer D and writing here, if a solid sphere, if you use hollow sphere, you will get different result. 48th. The speed of a homogeneous solid sphere after rolling down an inclined plane of vertical height h from rest without sliding is, it means speed of a homogeneous solid sphere. Now it is clearly mentioned that it is solid sphere. When it will come down, its potential energy will convert into its translational kinetic energy plus rolling kinetic energy. What is translational kinetic energy? Half m v square. What is rotational kinetic energy? Half I. For solid sphere, I is 2 by 5 m r square. Half I omega square. Omega square means v square divided by r square. Cancel this r square with this r square. 2 with 2. M with m. So what we are getting? GH is equals to, take v square common, half plus 1 by 5 means v square into 7 by 10. So v square is equals to 10 GH by 7. Therefore, v should be root 10 by 7 GH. So we are going with option A. A solid sphere, disk and solid cylinder, all of the same mass and made of the same material, are allowed to roll down from rest. I discussed with you in starting of this unit of crash course that the object which has more radius of gyration, it will come last, because radius of gyration was in denominator. What is happening there? We discussed that when an object is rolling down, its potential energy is converting into two type of energy, half mv square plus half I means mk square. Half I omega square means v square by r square. Cancel m with m with m. So what we are getting, 2gh is equals to v square into 1 plus k square by r square. So speed will depend upon radius of gyration. 2gh are constant in this case, and radius is also same mass, same material, means volume is also same, mass is same, so radius should be same. K will decide who will come fast. If k has more value, V will be less. So first we have to calculate k. First we are going for solid sphere. mk square, solid sphere. What is solid sphere? Moment of inertia 2 for solid sphere, 2 by 5 m r square. Cancel m with m. So what is k solid square, ks square is equals to 0.5, or we will calculate this k by r square. Ks square by r square is 0.4. Now we are going to calculate for disk mk square. For disk it is mr square by 2, means 0.5 mr square. So for disk we are getting kd square by r square is equals to 0.5. Now for solid cylinder, for solid cylinder again half mr square. So for cylinder, kc square by r square is again 0.5. So less value is for sphere, so sphere will reach first. So we are going with option A. A solid spherical ball rolls on a table. Ratio of its rotational kinetic energy to total kinetic energy. For solid sphere, we just solve the ratio of, here we take calculation with translational kinetic energy. Here we need ratio of rotational kinetic energy, means half I omega square upon total half I omega square plus half m v square. Divide whole equation by half. So half, remove this half. For solid sphere, I is 2 by 5 m r square. Omega square is v square by r square. So 2 by 5 m r square plus m v square. M. Remove this r square with this r square. It is omega square, means v square by half. It should be 2 by 5 m r square into v square by r square. So cancel this r square with this r square. So what we are getting? 2 by 5, and remove, cancel this v square also, divided by 2 by 5 plus 1. Cancel this v square, v square, v square. So what we are getting now? 2 by 5 divided by 7 by 5, 5 with 5. So we are going with D, 2 by 7. For a hollow cylinder and a solid cylinder rolling without slipping, which of these reach earlier? C, for which K is less? For hollow, mr square is equals to mk square. So K is R. For solid, it is for hollow. For solid, half mr square is equals to mk square. It was for hollow, it was for solid. So for solid, r by root 2. It was for hollow, r is same. For solid, so value for solid is less, so solid will reach first. So we are going with A. Point P is the point of contact of a wheel on the ground. It is ground. It is point of contact on ground. We are talking about this point P. The wheel rolls on ground without slipping. The value of displacement of P when wheel completes half of rotation. Half of rotation means P will reach there at this point. So this distance in half rotation should be half of circumference, means 2 pi r by 2. So it should be pi r. We want to calculate this distance, means initially P was at A, now P is at B. Take this point C. BC means diameter. Radius is 1, so it is 2. We want to calculate this displacement. So what is? We can use Pythagoras theorem. X square is 4 plus pi square r square. R is 1, so it is pi into 1 means pi. So r square will become 1. So what is x? Displacement is root 4 plus pi square. So going with B. A solid cylinder of mass m and radius r rolls without slipping. Solid cylinder is coming down, so its kinetic energy is converting into rotational kinetic energy I. For solid cylinder, half m r square. Omega square means v square by r square plus translational kinetic energy half m v square. So cancel m with m, half with half. No, we cannot cancel, because we can cancel if we write half into 2. We can cancel now this half. So now what we are getting? 2gh is equals to half v square plus v square, 3 by 2 v square. It means v square is 4gh by 3. This implies v should be root 4gh by 3. So we are going with B. So it was all about this unit. End of your third unit of crash course. Thank you.